A very good evening, all of you who are present here today. Here we are going to experience another webinar organized by the Sri Lanka Association for the Advancement of Science, Section E1, in collaboration with the Physics Student Society of University of Kelaniya. Will be under the topic of supercapacitors. To start off the session, now I would like to briefly introduce our speaker today. Dr. Aruna Ranavira earned his Bachelor of Science Honours in Physics from the University of Kelaniya in 2006 and PhD in Electronics and Radio Engineering from the Hanki University, South Korea in 2017. Currently, Dr. Ranavira is affiliated to the Department of Physics and Electronics, University of Kelaniya as the Senior Lecturer. Dr. Ranavira is a member of IEEE since 2009 and a member of International Union of Radio Scientists, URSI, since 2018. He is a life member of SALS from the 2016 and served as the president of the Section E1 in 2020. His current research interests include the wireless power transfer, metamaterials, wave propagation control, and supercapacitor-assisted power electronics. He is guiding us for organizing this type of activity as the Senior Treasurer of the Physics Student Society of the University of Kelaniya. He contributes immensely to advancement of the science and technology of the country in various capacities. Now, I would like to invite Dr. Aruna Ranavira to start the session.
Thank you very much for kind introduction.
Okay, thank you, sir.
And good evening to everyone. And it is very nice to do this type of webinar, especially today. Today's the World Environmental Day, June 5th. So we are going to talk about ultimately how these supercapacitors effectively utilized for photovoltaic energy harnessing. So these days, this kind of hot topic, when we consider the environmental sustainability, it is a very nice topic to talk in like today. Actually, we don't plan to have this in the World Environmental Day, but it is a kind of coincident. So this webinar was actually delayed by several times. I think we planned to have this earlier, but anyway, finally it coincidentally lies and organized today, that World Environmental Day. Okay, let me turn off my video and share my screen. Okay, let me stop my video from here, just share the screen. Okay, hopefully you can see my screen clearly now. Yeah, can you see my screen?
Yes, sir.
Okay, again, thank you very much for giving me this opportunity to share some of my thoughts on supercapacitors and some research on supercapacitors that we are currently engaged in at the University of Kelaniya. So when we talk about the supercapacitor research, so there are two major directions that we can carry on. One is developing activated carbon-based material. That is actually material science-based approach for developing more efficient supercapacitor devices, optimization of the material. The other direction, the second direction, is utilizing this supercapacitor in various electronic circuits for better optimization of electronic circuit. So my research direction is this second one, utilizing this supercapacitor, particularly in as an energy storage device in off-grid PV system. So here actually the off-grid means we are utilizing this in standalone That means the photovoltaic system that is not connected to the national electric grid. So let me uh, uh, briefly share my thoughts on the current ongoing research. So these slides are actually I prepared for some webinar that I have done for South Korea, some researchers. So therefore, I'm not going to cover everything in the slides, but I want to share some important basic fundamental concept on supercapacitors and how specifically there is a concept called supercapacitor assisted loss management theory or loss management concept. So that is the key point that I have to emphasize, or that I want to share with you some ideas on that, and then how that can be used to improve the efficiency of off-grid photovoltaic system. So, so this is again a kind of uh, extension of a basic theory in physics textbooks into the real world application. So all of my research actually, the wireless power transfer, metamaterial, whatever, what basically I'm doing is extending very simple theory into a useful real world application. So by sharing this, my view on this, I want to show how you can extend some known theory into a useful real world application, taking this supercapacitor as an example. Okay, so these are the content of my presentation. So I will start directly with some fundamental concept of energy storage devices. So when we work with electronics or electricity, so we need power. So these powers will be ranging from the different values. So if we talk, so the power ranges that we are currently working on is actually uh, uh, is in kilowatts range, but when we, in generally, when we consider if we want to operate intelligent pipe goods, so we have to work on watts to few 100 watts to few megawatt range. And when we go for application like automotive application like hybrid electric vehicles, so electric vehicle, so we need a power of tens of kilowatt, so a little bit lower than that few megawatt. And then so nowadays this because of this smartification, this wearable devices and those portable electronic devices, there is very huge demand for small scale electronic devices where we work on microwatt or watt scale circuit. So to operate all of these devices, definitely there should be a kind of energy source device. So, so, so if we utilize the national electric grid, so we are utilizing the energy storage in water tanks or burning fossil fuels, we generate electricity. So there is no actual storage device. But when it's come to the real world application, so we need to have a kind of mechanism to store this energy in order to utilize them in these portable electronic devices or automotive applications or intelligent white goods. So basically, when we talk about energy storage devices, there are different energy storage devices. So the most famous device is the battery. So electrochemical battery or lithium-ion battery. So there are actually recently some emerging trends of the sodium-based, electrode-based, another type of batteries. So I'm not going to actually talk about those things. And then we have this supercapacitor banks. That is the particular topic that I'm going to talk today. And then flywheels, fuel cells, compressed air, or superconductive magnetic energy storage are also there as a kind of energy storage devices. So out of them, actually, yeah, batteries are the traditionally the most famous thing. And then different application, different types of these devices, these storages are utilized to store energy. And when we want to use those devices, we have to turn the power stored in those devices, energy, not the power actually, the energy stored in those devices to flow into the device. So supercapacitor is also a kind of energy storage device. Okay, let me go to the next slide. So here, I just want to explain some simple physics. So energy storage device, or we abbreviate this as ESD device. So ESD. So here, this very simple circuit diagram shows a kind of energy storage device, which is symbolized with this voltage source and its internal resistance, which is connected to the external load RA. So very simply applying the Ohm's law, you can derive this expression for current is this voltage divided by the total loop resistance, that is the addition of these two. And then the voltage drop across this resistance is going to be this value. So therefore, the power delivered to this load, this particular external load, RL. So we can write this using this two. You can write this as this one. And at the same time, the power loss which is happening inside this energy storage device. So this is not just supercapacitor, any type of energy storage device. The power loss happening inside this energy storage device can be written using this very simple formula that we learn in our junior science classes, I squared R. So that is going to be the current flowing in this branch, that is IL squared, and multiplied by the internal resistance of this energy storage device. So that is going to be this one, and we can modify, or we can actually express this as PL R internal divided by RL, this last expression. Let me take kind of laser pointer here. Yeah, something like this. Okay, so therefore, useful voltage appearing at the load keep dropping as the internal resistance increase. So if this R int, if this value is going to be increased, because this PL and RL, we can consider them as a kind of a constant value. So therefore, if actually if we can so PL is this one. So these two are kind of constant value. But if we increase this R in, so you can see that this power loss is also going to be increased. Therefore, as far as energy storage device is concerned, so we prefer higher open circuit voltage and low internal resistance as much as possible. So by doing some material development, what scientists trying to do is to lower this. One of the things that they want to do is this lower the internal resistance. So in rechargeable batteries, one of the things that we can observe is this internal resistance keep decreasing with discharge. So that means when the battery discharge, its internal resistance is increasing. So if the internal resistance is increasing, according to the equation here, the power drop inside this internal resistance is also increasing. Therefore, the power delivered to the load is going to be dropped. So when it comes to the supercapacitor, so one of the feature that is available with a supercapacitor is low internal resistance. So actually, the actual value is a kind of a fraction of millihertz. So therefore, they are able to supply a large amount of power, but for a very short period of time. So that is one of the things that this supercapacitor make itself suitable to be used as an energy storage device. So we will talk this features of supercapacitor a little bit in other slides. So, so some of the other two parameters. These two parameters are very important parameters when we talk about any energy storage device. So when we evaluate the performance of energy storage device, there are two important parameters. One is energy density, the other one is power density. So when we talk about the energy density, actually there are two types, volumetric and gravimetric. So the energy density is the amount of energy stored in a given system per unit volume. So this is measured in joules per liter or joules per cubic meter, or else watts. If we measure the energy in terms of watt actually, so we can specify that in terms of watt also, watts per liter or watts per cubic meter. So when we actually talk about the energy density in terms of specific energy, so that is actually called gravimetric energy density. So this is the amount of energy stored for unit mass. So this is specified in joules per kilogram. And when it's come to the power density, again we have the volumetric power density and also the gravimetric power density. So the power density, volumetric power density is the maximum amount of power an ESD can deliver per unit volume. So the power is the actually rate of doing work actually. That is what is specified with watt. So here actually, when it comes to the energy, there is the time parameter, watt hour is there. So here just the watt is there. So watts per cubic meter, or if we consider a unit mass thing, then it's going to be a specific power. So yeah, in order to give you a good idea how battery and supercapacitor is compared using these two terms, can be illustrated like this. So when it comes to the battery has a very good specific energy. So that means the watts per kilogram. So the amount of energy that we can store in a battery is very large as compared to the capacitor, supercapacitor actually. So, but in case of specific power, that means in a short duration of time, the amount of power that we can deliver from a capacitor is large. So, if you think in terms of water, from the battery, this opening is very small, so that the specific power that we can deliver is small, but we can keep large amount inside. But when it's come to the capacitor, this opening is very large. So therefore, very in short duration of time, we can flow much amount of water. So you can actually keep this in mind in order to understand the difference between battery and supercapacitor in terms of specific energy and specific power. I hope you may understand these things up to some point. Like this is actually a very fundamental concept when we talk about any energy storage device. And okay, then another two important parameter is cycle life and cyclic energy density. Cyclic life very simply means how many times that we can charge and discharge a supercapacitor before the performance decreases to an extent that it cannot perform the required function. So this is used as a measure of energy storage device ability to withstand a repetitive deep discharging and recharging cycle using the manufacturer's cyclic charging recommendation. Not only a supercapacitor, any type of energy storage device, when you charge it from another power source, for example, if we connect it to the power supply, so there is a manufacturer's recommendation. So the current should be this much of maximum level, it should not exceed. So utilizing that one, so the number of times, so one time we charge, then we use it, again we charge it. So how many times that we can charge? So that is called cycle life. And then if we multiply this energy density and cycle life, that is actually the unit of that particular measurement, watt-hour cycles per kilogram, if we consider the gravimetric energy density. But if we consider the volumetric energy density, that is going to be watt-hour cycles per cubic meter. So that is another good measurement for evaluating the performance of energy storage device. Yeah, these measurements, these parameters are used for comparing different types of energy storage device. And self-discharge rate is another thing. So this is actually, as its name implies, a measure of how long that an ESD can store or left unused until its performance degraded. So this is actually measured by placing the battery or a supercapacitor or whatever the energy storage device on shelf at room or elevated temperature by monitoring its open circuit voltage. So usually this open circuit voltage is going to be decreased and it is going to be decreased. So this self-discharge rate is another important measurement. Yeah. Why we can use this capacitor as an energy storage device? So here you can see, capacitor with internal resistance. Usually for the internal resistance of the capacitor, we given this parameter is called equivalent series resistance, or ESR. So capacitor will usually the symbol of capacitor is this one, but when we go for the actual model, that is going to be much complex than this. But when we thought a capacitor as an energy storage device, the symbol that we use to symbolize this energy storage device is the capacitor symbol with this type of series resistor. So therefore, this VCO is the initial DC voltage of the capacitor when we charge this. As you know, capacitor, by connecting a power source, that means connecting a battery, you can charge it to up to certain voltage, depending on the voltage rating that is printed on the surface of that particular capacitor. Not only a supercapacitor, but also any type of capacitor. So if we consider that initial voltage that we charge this capacitor as VCO and the equivalent series resistance as RC, and if we connect this one into a load resistance of RL, and there is a switch to control this current, so this is actually on at t equals 0. So using the basics physics principle, you can show that the energy that you have stored in the capacitor is equal, by charging it to this VCO value, is going to be equal to half CV squared. So I think this is advanced level physics. You already know this very simple equation. So if you close this switch at t equals 0, initially there will be a current flowing through it. So that current can be calculated as this voltage divided by this total loop resistance, that is the addition of this RC and RL. So you can, I think you can very easily understand this one. So when this load is very small, the value of ESR determine the maximum possible current. So if this value is very small as compared to this RC, so this will determine the maximum possible current. So in this type of very simple circuit, actually, there is a parameter called time constant. So when we actually develop the equations for charging and discharging of capacitor, this will came into the action. So the time constant of the circuit is defined as the total loop resistance multiplied by a value of capacitance. So capacitor has a parameter called capacitance, which is measured in farad. Usually in if it is not a supercapacitor, its value is in the range of microfarad to picofarad somewhere. So ultimately, what I want to say is the time constant is the a multiplication of this resistance, total resistance values in capacitance value. So that is one of the key things that we need later on. So capacitor discharge and energy released to the load. So, so using the physics, some principles. So this is actually a capacitor discharge curve. So if we kept this capacitor connected to this RL, if we draw the voltage drop, voltage across the capacitor with time, so it will be decreasing like this. So the exact equation, don't worry about actually this equation, so you can easily derive. So this is not actually the lecture, some kind of lecture that I am doing in the university. So I want to share some thoughts, therefore. So I'm not going to actually show some how to derive those things. I think you may have chance to learn these things in your if it is in the Kelaniya University. I think it's in third year electromagnetic class. So probably you may have learned it in electric circuit fundamental in your first year. I'm not sure in which course you are learning this one. So you can get the equation of this one like this, and here there is a exponential term e to the power minus t over RL plus RC over C. So there this t over the time constant is there, and at the same time, the energy released to the load, that is, there is external resistor RL that we connected to the capacitor. So if we monitor the energy or the that is delivered to that particular load, we can draw that graph like this. So if this ESR is significantly large as compared to the external load, the transfer efficiency, transferring power to the external load is quite low. For a normal capacitor, uh, basically we have finite large value of ESR. So therefore, there is a leakage current wasting energy as a heat in normal capacitor. So when it goes to an electrolyte capacitor, those are the types of capacitor that you are attached to filter out in DC rectifier circuits, linear rectifier circuit. So the value of in the capacitance values are in the range of nanofarad to microfarad. So they can retain charge from microsecond to few minutes, but few minutes is not enough to treated them as useful energy storage devices. So when it comes to the supercapacitor, so few thousand of farad or leakage current of few microampere to milliampere will be created because of lower, very low ESR, equivalent series resistance. So therefore, they allows them to use as short-term energy storage and delivery device in electronic system. So therefore, this small, significantly small value of ESR make them to be used as energy storage and delivery device in power electronic circuit. So that is the feature that make them suitable to be used as an energy storage device. Okay, so okay, this is another important graph actually. So this graph is called Ragon plot. මේ graph එකට කියනවා Ragon plot එක කියලා. This was developed by a scientist called Davis V. Ragon. So this is also utilized to compare different energy delivery capability options for different type of energy storage devices. So therefore, yeah, let me explain this a little bit. So this y-axis is gravimetric energy density, that is watt hours per kilogram, and x-axis is gravimetric power density watts per kilogram. So usually these energy storage devices, I previously mentioned, there are batteries, there are supercapacitors and fuel cells and flywheels and so on. So there are different types of energy storage devices. So they came in different physical sizes, different types, and with different parameters. So in order to better compare them, මේවා හොඳම එක තෝරගන්න නම් මේවා හොඳ විදිහකට කම්පෙයාර් කරන්න ක්‍රමයක් තියෙන්න බෑ. There should be an efficient way to compare them effectively. So in order to do that, this Ragon plot is utilized. So that I previously mentioned, to axis will be represent this gravimetric power density and gravimetric energy density. So therefore, we need to have, as far as energy storage device is concerned, we need to have a very large energy density and also a large power density. So therefore, we have to go along this axis into positive direction as much as possible, and also in the y-axis into the positive y direction as much as possible. That means we have to go along this diagonal into this direction. So one should try to develop systems or energy storage devices that can be placed at the northeast corner of this chart. So that is what is expected by developing a new type of materials and so on to introduce new supercapacitor or whatever the energy storage device. So there are some this dash line which are shown in this graph actually. So those sloping lines are called the isotomes of characteristic time constant. So they actually indicate the relative time taken to get the charge in or out of the energy storage device. Yeah, so this is actually this Ragon plot is one of the important way of comparing different energy storage devices to select some better devices. So you can see actually the batteries have good energy density and capacitors have good power density. So that what you can observe here. Okay, let me I hope you may have good some idea on this graph. And okay, this is a comparison of supercapacitor and electrolytic capacitor. So basically this world of electronics, electronical when we talk about electronic circuit, there are two types of devices. There are two types. The devices can be categorized into two categories: active devices and passive devices. So the category of passive devices are based on three different electronic devices: the electronic component, capacitor, inductor, and resistor. So out of those three passive devices, capacitor usually uses short-term energy storage device, but we want to make it a long-term energy storage device as much as possible in order for them to be applied in photovoltaic energy harnessing. So this is a comparison of supercapacitor and electrolytic capacitor. So these are normal capacitors. So these are electrolytic capacitor. This is normal ceramic capacitor. These two, and so you can see these are actually same canister size. So canister means actually the physical arrangement that the capacitor is developed on. So when you look at this supercapacitor, the energy that you can observe is joules, but here millijoules. So if you go for, this is 150 farad Maxwell brand supercapacitor. This is 330 microfarad. So the energy storage capability is 26.4 joules. This is normal electrolytic type capacitor. But when it goes to the supercapacitor of the same physical size, you can store around 20 times larger energy in this capacitor. So typically, supercapacitor, we get approximately 1 million times bigger capacitance. Imagine. So before around 20 years ago, actually, there was nothing called supercapacitor in the market, actually. But nowadays, these are abundant, as in other electronic devices. So imagine this capacitance value is jumping from microfarad into farad. So that is a jump of 1 million. So therefore, so we can do something with this particular jump of this capacitance value, but there is one disadvantage. The DC voltage rating is very low. So you can, in this electrolytic type capacitor, you can see that 200 volt you can apply, but here for this 150 farad, the DC voltage rating, you can see here like 2.7 volt. So that is the typical value or the maximum, probably the maximum, but I think 3 point something is available also in the market. But that is the range that we can go for the DC voltage rating. That is one disadvantage. But anyway, we can store more energy in supercapacitors. Okay, let me go to the next slide. Okay, this is another data set, actually, comparison of electrolytic and some supercapacitors. So I'm not going to explain this one. What this data shows is, in general, supercapacitors have lower ESR than electrolytic capacitor, but their DC voltage rating is very low. So that is the same fact that I highlighted in the previous slide. So therefore, I will skip this one. And then what are these supercapacitors actually? So you may have some idea now, because time is past, but I don't want to actually do this fast and finish this in rushly without giving you any idea. So I want to give some message. That's why I'm doing this very slowly. As I previously mentioned, there are large number of slides, around 60, but I don't want to do them all. But the basic idea, why these supercapacitors are important. So that is the message or the thoughts, my thoughts that I want to share with you all. So supercapacitors are ultracapacitors are a type of capacitors with very large capacitance within the family of electric double layer capacitor. Why this is called electric double layer capacitor? So inside the supercapacitor, actually, we have two capacitors. Okay, I will explain that just in 2 slides. And they can store electrical energy quickly and discharge slowly. They can store energy quickly and discharge slowly. Faster discharge rate than battery. That is why specific power is very high. In many applications, batteries we cannot replace because this faster discharge rate. For a single cell form, so supercapacitors, we can buy it as a single cell or a collection of it. So when we go for a collection, we call it a capacitor bank. So for a single cell, the capacitance is fractional farads to several thousands of farad with voltage range from 0.7 volt to about 5 volts. And this is very basics about the capacitor. So if you have parallel plate capacitor, you can write the capacitance of this device epsilon r epsilon naught a over d. D is the distance between the, and then this a is the surface area of one of the electrode, and these two are electric permittivity, the relative permittivity of this dielectric medium between these two plates, and this epsilon naught is the electric permittivity of the free space. So this is the basic capacitor. I think you all know that capacitor is made of two parallel metallic plates separated by a dielectric material. So in order to have large capacitance, what we need is we need to have large area, and also we have to decrease this D value, the plate separation, as much as possible. And then the charge that we can store here can be written as Q equals CV, the capacitance value and the voltage applied here. So therefore, a bigger capacitance and higher voltage make bigger charge storage capacity. So the energy storage of a capacitor we can write using this very simple equation again, E is equal half CV squared. So the energy storage is proportional to the square of the voltage. So with the supercapacitor, so this instead of this electrode, actually the large area material which porous nature means some type of powder or type of dielectric material will be put between these two electrodes. So thereby the surface area will be increased. In order to jump the capacitance value from microfarad to the farad value. So this is a structure of the supercapacitors. It is supercapacitor module, but when it's come to the single form, so the current collector and electrode material. So these electrode materials are kind of porous electrodes. So we have a kind of separator. So because of this separator actually, so there will be two capacitors that is formed within one supercapacitor cell. So this is again structure-wise a comparison of normal capacitor and supercapacitor. So this metal electrode actually are activated carbon-based electrode in porous nature. So this is where some of this is a point where some of the research happening in Sri Lankan universities, the activated carbon-based electrode material development for much more better efficient supercapacitor development. But so my research area is not that one, so therefore I'm not going to actually describe those things. So therefore actually with these two capacitors connected in series like inside one thing, so therefore the working principle, the charge separations happen. When it discharged, these ions again randomly distributed. So I think yeah, this is not the main thing that I want to highlight in my talk today. So therefore I do not want to spend much time at these sliders. So supercapacitor is a kind of electrochemical storage device. So therefore it has a property of a battery as well as a capacitor. Because of this particular structural arrangement, and this is a double layer device, so there will be two capacitors inside. They are connected in series. So that is actually highlighted in this one. And so because of this electric double layer capacitor, so they will, so previously in the Ragon plot, electrolytic capacitors are here, fuel cell are here, and different types of range of batteries are available here. So there is a huge gap between these batteries and normal capacitors. So supercapacitor came into the picture in order to fill this gap between these batteries and also the capacitors. So that is what happens if we look at the Ragon plot view with the introduction of this supercapacitor. So this is again a comparison of supercapacitor and batteries. So this is a normal energizer battery. So you can see the internal resistance is keep increasing as it discharge. This depth of discharge means as time passes, the storage is going to be lost because of discharge. So when it discharge, the internal resistance is increasing, thereby the battery will not be able to provide power. Then the supercapacitor, in contrast, we have constant and very small value of internal resistance. So supercapacitor with constant and very low sorry, ESR can deliver much higher power into a load than an electrochemical battery where ESR keep increasing with the discharge. So that is what the message that I want to emphasize with this slide. And with this material research, actually, there is a recent advancement of these different supercapacitor families. So there are 3 different families now in the market: symmetrical electric double layer capacitors, hybrid supercapacitor. So there is one electrode based on lithium compound. The other thing is called kappa batteries or capacitor batteries or pseudo capacitors. So they have both the properties of both the electrochemical batteries as well as in capacitors. So therefore, with kappa batteries, we can go for much more capacitance values. So 3 different supercapacitor of these 3 categories are shown here. This first one is a capacitor battery of 40,000 farad with DC voltage rating of 2.7 volts. The middle one is a hybrid supercapacitor with 7,500 farad with 2.8 DC voltage rating. And the third one is a 300 farad capacitor, supercapacitor of symmetric EDLC with 3.0 voltage rating. They are in the same physical size, but with the recent advancement of material science, this made possible. Yeah, the same thing actually drawn in the Ragon plot. Same thing is drawn here in the Ragon plot. So the capacitor battery with actually normal supercapacitor appearing here, then hybrid and capacitor battery, so much more capable device. Previously, I mentioned that we have to go along this diagonal line in order to have better devices. So with this capacitor batteries, much more capable devices came into the reality. Yeah, okay. And then let me skip this slide. And then this is a summary of recent advancement. Okay, let me skip this slide also. These are all some practical aspects in different point of view. And these are some advantage and disadvantage of supercapacitor as an energy storage device. You can see the fast charging, but very low specific energy, and longer life than battery, but with very low DC voltage rating. They can withstand any temperature between 30 to 65, whereas battery has much more range in this minus side, whereas actually battery has lower range, but here this is actually minus 30 to 65. And also comparing to the battery, the weight is small, and we can store in short physical area as compared to the battery. And also they have very fast transient response. So therefore they have advantage as well as disadvantage for each of the property. And these are some of the application that are emerged into the commercial level market with supercapacitor. Okay, Let me go to the thing that I want to share actually. Traditionally, supercapacitors were used in automotive, some industrial, and also some consumer electronic applications, as well as energy-wise application. But they will be utilized as power backups in uninterrupted power supplies, utility voltage stabilizers, or wind turbines or PV system. So that is actually there is a traditional way, but here also in PV system also they will be utilized as a power backup. But what I want to emphasize here, uh, uh, a different thing. Let me go into the next slide. So this is again our very simple circuit. Capacitor is connected to a battery through a switch. So if we make this capacitor a supercapacitor, so with very large capacitance inserted into the resistive circuit loop, what supercapacitor does is they create very large time constant circuit where charging and discharging process can be easily controlled with low speed switches. So this switch can be a mechanical switch, but we need to control this one with electronic switch. That means a MOSFET transistor. So that is the basis for unique novel circuit topologies addressing a well-known circuit issue such as energy conversion efficiency and the protection against transient and rapid energy delivery. So, these are the application supercapacitor assisted. So these applications are called supercapacitor assisted technologies. So this supercapacitor assisted term is abbreviated as SCA, SCA. So we have supercapacitor assisted PV energy harnessing and high energy linear DC-DC converter or SCALD. So at Kelaniya, actually, we are doing both of these things, and also the SCA LED concept, low voltage DC LED lightning for DC microgrid application. So these three actually, more or less, actually, the first one is the one we engage. One of my actually first PhD student, he is working on this extensively, and extension of his work is actually related to this SPI LED concept. And this is also something that we have published one conference paper. But for this, actually, we are doing some extensive work, and then there are some applications. So all of these applications are based on a concept called a supercapacitor assisted loss circumvention, or sometimes we call loss management theory or concept. So that is the final point that I want to highlight. Let me talk about this particular concept a little bit in detail in the next slide. Okay, this is the supercapacitor assisted loss circumvention theory. So here we have a battery, and then we connect a capacitor. So using this very basic equation, the energy storage, if we connect voltage source of V into the capacitor of capacitance C, the energy that is stored in this capacitor in Coulomb can be calculated using this equation. That is going to be equal to CV. And yeah, for this same process, we can actually write these two equations so that the capacitor voltage can be written in terms of its time constant R and C like this. So if the capacitor is charged from 0 to V volts, the energy storage is going to be equal to QV over half. Utilizing actually this CV squared over half equation and QV equals CV, you can very easily get this one. So instead of what we what we remove here is this Q term. So instead of Q, if you apply instead of this C, if you apply Q over V, you can see that this EC is going to be equal to QV over half. So therefore, this is the energy storage, and if we consider the energy loss, that is also using the very simple textbooks theory of physics. You can show that the energy loss is going to be also equal to QV over half. So therefore, if we provide a QV of energy into a capacitor, theoretically, the maximum possible level that we can store inside the capacitor is QV over half, where if we have ideal electrochemical battery, the battery is capable of storing the all the amount QV. So therefore, the capacitor charging process is efficient only at 50%. The remaining 50% is wasted. So with the supercapacitor assisted loss management theory, what we do is that wasted amount 50%, some of them will be recovered. So that is what is called loss management theory. What we do is actually, in order to do that practically, what we do is, this is normal capacitor charging loop. So what we do is we replace capacitor with supercapacitor with pre-charge, not an empty supercapacitor. It has to be charged up to a certain value. So if we do that using very simple physics again, very simple physics, what we can show is, so before we add the supercapacitor, look at this slide. So the efficiency is 50%. So if we add a supercapacitor, and also we need to add, so here actually this RT here represent the total loop resistance. So in order to utilize the wasted energy, apart from adding this supercapacitor, we need to insert a kind of load here. That should be a resistive load. So here what we do is we add a resistive load into this capacitor charging loop. Thereby, we can go for efficiency value that is greater than 50. So from that wasted 50%, some of the energy will be utilized by this resistive load. So that is what is called supercapacitor assisted loss circumvention theory, loss management theory, loss management concept. The different names are there. So these are actually not very difficult equation. So very easily you can understand if you have the basic electric circuit fundamental knowledge. With that, actually, you can very easily get those equations derived. And also, you can see that there are some, in every slide, actually, I mentioned some reference materials. So if some special, or those who are following special degree physics, or someone who are interested in this area, you may refer to these references. And this is the supercapacitor loss management concept in graphical form. So adding this RL, the efficiency will be increased. Actually, there are several parameters that we have to consider. This M and K is defined as a free charge factor and power supply over voltage factor. But I'm not going to actually go into the details of that theoretical analysis. So usually what happens is, if we have just a capacitor, only the charging efficiency is 50%. By adding a resistive load into the capacitor charging loop, some of the wasted energy can be utilized. So that is what we actually did in off-grid PV energy harnessing system. So let's see how we apply this into uh, the energy harnessing. So this is what we do with supercapacitor at University of Kelaniya. So this is not the fundamental research. This is applied research. So supercapacitor as energy storage device in PV energy harnessing. So countries where national in our country the national grid is heavily depending on hydropower and fossil fuels. So in the dry season, lack of water intakes makes trouble in hydropower generation. And also, we are country located near to the equator and sunlight is abundant and freely available throughout the year. Therefore, there is a very high demand for solar energy as an alternative or regenerative energy source. So therefore, with that in mind, so we are trying to apply this supercapacitor assisted loss management theory to standalone or off-grid PV system. So typical PV system, we have a PV array. This is the solar cell. Then we have charge controller. From charge controller, we can drive DC load. We can store some of the energy in the battery bank. So if we want to drive AC load, what we need to do is we have to have a DC to AC inverter. And then from distribution panel, we can drive AC load. So there are a lot of conversion process. So each of them wastes actually considerable amount of energy. So, and the one more thing. So in all of these PV systems, we have to have kind of maximum power point tracking. So in electric circuit fundamentals, there is a circuit called maximum power transfer. So from source to load, if we want to transfer maximum power, so the impedance of the source should be matched into the load. So that is called power. So that is what is happening. That is what actually happening with this the maximum power point tracking circuits. So that should also be assured with this new concept. So therefore, so in as I previously mentioned, the supercapacitors are already utilized in PV energy harnessing. But what they did is the PV array is here, DC-DC converter is here, and then drive to AC DC-AC converter and drive the AC load, or DC-DC converter to battery, and also store some of the energy in supercapacitor bank. But this is the traditional way. But what we did is, in our method, what we did is we take this type of energy storage device and inserted in between PV array and charge controller. So we insert supercapacitor bank in between PV array and this charge controller. So therefore, that will implement a capacitor charging loop with kind of useful resistive load. So that is where we apply this supercapacitor assisted loss management or loss regain theory, loss management or loss reconvention theory. So with that, actually, these are some of the circuit diagrams inside the system. So depending on the time constant, I think, so if we can talk much more time, but your interest may be lost because I'm talking much more theoretical concepts. So therefore, let me go deep. So these are some of the things that developed by my research assistant, actually. So what we achieve is with this supercapacitor loss circumvention theory, the efficiency of typical solar energy harnessing, we were able to increase that by 90% up to 89%. And also, we implement that actually what we call the maximum power point tracking, and that also we achieved here certain results. So I don't want to actually now let me check the time. I think Yeah, it's more than 1 hour. I think I should not talk much more things, theoretical things. Then your interest might be lost. So what yeah, these are some of his experiment and then the improvement, and also I previously mentioned that this supercapacitor loss management theory can be applied in variety of application. So one thing, one of my other student did was this is called and also the same research assistant who is doing PhD is working on this style ED concept. Yeah, ultimately, yeah, let me finish like this. So, in typical photovoltaic systems, so there are grid connected systems. So we cannot address those things, the problems on energy storage in those systems with supercapacitor. But when it comes to the off-grid system, that means standalone systems, so most of the solar energy is wasted. So if we utilize supercapacitor using this supercapacitor assisted loss management concept, some of those wasted energy can be recovered and usefully utilized. So that is what very simply we want to do. So in order to do actually, starting from those basic physics, various theories have been developed. So again, the theory that we utilize is not a very complex theory, very simple theory. So we extend that into a useful real world application and make it possible. So that is what we have done. So in future, I hope that this type of emerging application will be emerged. So if you really want to experience these things, yeah, you need to read some stuff related to these things and do research. So if you I think most of the students that joining this webinar today are first year or second year students. So if you want to do a special degree or master in Phil, so you may actually do some sort of small research in this area and get a better understanding. So other than that, actually, if I whatever the way, if I explain these things, you may not be able to understand and your interest may be lost. So that is why I don't want to keep waste time on explaining these things. But if you have some problem, actually, you may email me or you may discuss me regarding this supercapacitors and their application. So this is not a fundamental type research. This is applied research, and so our research, finally, I want to acknowledge all my research was supported by a head RIC grant funded by Sri Lankan government. So I am acknowledged him for the financial assistance, and also especially I want to acknowledge one of the Sri Lankan professor, Professor Nihal Punaratna, attached to the University of Waikato, who is the collaborator for this supercapacitor research, and he's the inventor of this Scaldo and several other supercapacitor assisted techniques. He's one of the, he's giving a kind of immense support to us to conduct this research. And also the members of our research team at the University of Kelaniya, and also my research assistant, Asun. He's the one who worked on this supercapacitor assisted PV energy harnessing area, and also Tarindo, Ishara, Hiruni, and Pugudu, the other research assistants. Yeah, they are the driving force behind all these research works here at University of Kelaniya. And finally, I would like to thank SLAS and also the Physics Student Society giving this opportunity to share this important topic today at this World in Environmental Day. Okay, thank you very much.
As we have come to the end of this session, Now it's time for question and answers.
Recording
All the
stopped.
participants are welcome to ask any questions, or you can drop the questions in the chat box. All are welcome to related to our topic.
Okay, there are a few questions actually in the chat box. So can we retro existing PV system with supercapacitor? Yeah, restore. For an existing PV system, yeah, it is actually difficult because if it is grid connected one, you cannot touch the things because still on electricity board they have switches and all those things. If it is an off grid system, actually there are inverters and the system is already fixed now. So therefore, yeah, you can fix, but you cannot actually get the things done as you want. But the system has to be developed in this way. So this system is not commercially available yet, but we are trying to actually commercialize ultimately this type of system somehow. So once we commercialize, you may fix it, but for the existing system, yes, you can, but it is little bit difficult because everything is fixed inverters and every system has a particular arrangement. That's why. Yeah, I think that's the only question available in the chat box. Any more questions?
Okay, is there any more questions?
Okay, there is another question from Owen. When installed a supercapacitor between PV panels, does heat will influence its efficiency? Heat will influence the efficiency of solar panel also, but ESR of supercapacitor is very small. Therefore, heat generated by the supercapacitor is also very small. But there is a possibility for a little degradation. But as far as the solar panel is concerned, there are some ongoing research that the solar panels that if we can cool the solar panel where the solar panel is installed while having the sunlight, the efficiency of the solar panel will be increased. So that type of activity, I read some articles like that. So, but that supercapacitor module itself does not generate much heat because ESR is very low, but that has to be studied. That is another good point for you to do kind of research.
Okay, thank you, sir. Thank you very much, all the participants, for engaging with us in this valuable session. To mark the ending, I would like to invite Malki Ratnayaka to deliver the vote of thanks.
Thank you, Anne. First of all, I would like to thank Dr. Aruna Ranavira for joining us today in spite of his busy schedule and for all the knowledge he shared with us, and especially for guiding us to make this webinar more successful. Also, I would like to thank Professor Kalinga Mudali, the Dean of the Science Faculty, and all the chairs, organizing team, and all the members of the Physics Student Society who gave their contribution to make this happen. On behalf of the Physics Student Society of the University of Kelaniya, I thank all of you who have joined us today, and we hope you all have had a very productive evening and was able to get the maximum out of the session. Stay tuned. Thank you once again and stay safe.
Okay,